All right, so this one is Leetcode 199. This is a binary tree right side view. Right, so make sure this is recording and you can see it. Okay. Yeah, so essentially given some binary tree with some values, and this is not a binary search tree, so these don't have to be ordered in any way. Let's say you have 99 here. Yeah. So what you want to do is you want to return. So let's say you're from this right side and you're looking at this binary tree. You wouldn't see the 5, right? You would see all the elements to the right side of the binary tree. So what we'd return is an array that represents the values of the right side. So it'd be 1, 10, and then 99. Right? Because you would see this one, and this one. So this is a medium level question, but I think it's pretty simple if you know how to get the depths of the binary tree, which is actually pretty trivial to do. I guess I should have left that there. Yeah, so you're getting this one, and this one, right? Because that one's at the right side as well. It's the only node. So the first thing that came to my mind was create like a dictionary, and the dictionary should have like the depth of the depth as the key, and then every node in that depth as the value, and the value should be like in a list or an array. The dictionary should look like, in this case, we're at depth 0, we'll have node 1, just 1, and then depth 1, we'll have 5 and 10, and obviously these need to be ordered in the right way. 2, we just have 99, right? So if we have this array, we can literally just iterate through our values and then get the last element and then populate like a results array. And then this is actually a lot faster than most of the Python solutions that I've seen. So this is what I was going with. So let's go with this solution. So this is a recursive solution where we're kind of keeping track of the depth. So we'll have like a helper function to generate this dictionary for us, right? So we'll define our main function, I guess. Define right side BT. It's going to take in a root. It's going to take in a root node, and that's it. And we're creating a dictionary. Default value should be a list. So in Python, you could just import from collections, import default dict, or you could it just saves lines of code. You could also just use a regular dictionary and then create those values as a list, but I'm just going to use the default dict. So we'll say D is equal to default dict of list. So when you use default dict and you try to do something like this, d of 0 equals 1, or you just do d of 0 and 0 never exists in the dictionary, it'll automatically create an empty list. So that's kind of how default dict works. And you could also just do I don't know, put that dot there, ignore the dot. D of 0 dot append. And even if this is the first time you call it, you would enter 1 into that list. So that's kind of how that works. So yeah, so you have a default dict, and right, so if not root, then return, else. So what are we doing, right? So we need a results array to store the last elements, and we need need to populate D, right? So we'll do our helper function, which I'll just call DFS. I guess it's not even DFS. So I'm going from here, and then I'm getting the depths. Yeah, I'll just say get depths. Depths. And then this one's going to take in a root node, dictionary that we're going to populate, and a depth, which is going to be 0. Let me first call it. So that's going to give us this, and we're going to say for val in d.values, which are these lists that we're iterating over, the results that we're going to return, dot append the last value of these, right, which would be val minus 1, which would be the last element. And then we would just return res, making sure it's recording. Yeah. So now we can define our helper function down here. We'll call it define get depths. Taking a root node, dictionary, and a depth. So if not root, don't do anything. And then otherwise, we'll say the dictionary at that depth dot append that root node, the value of that root node, right? So we're at 1, or we're at 0, because we're starting at depth 0, and we're looking at root node 1. We would append 1 here, and then what do we need to do after that? We need to recursively call the function while we increase depth by 1. So we'll do get depth, and we want to insert the left element first so we can maintain our ordering. So get depths, root dot left, same dictionary because we're populating that dictionary, and then depth plus 1. Again, from the right side now, get depths, root dot right, d depth plus 1. Right, and that's it. So let's go over kind of how that will work. So we're at 0, we're at depth 0, and root with the value 1, so we append that on, and then we go call this function recursively, root.left, and we have 5, depth is now 1, so we append it here, and then we call it recursively again, root.left, which is 99. So before we even append this 10 in, we're going to have 2 and 99 there, and it's going to go back on the call stack and check that right has nothing, so it's going to go back in the call stack again, and it's going to see that that is 0 plus 1, which is depth 1. We're going to append the value there into our dictionary. And once that's all done, we'll have a dictionary that looks like this. And then we're going to iterate through the values and get the last element in each of these values, in each of these arrays, and append it onto our results array. And at the end, we're just going to return results, which would look like this. 1, 10, and 99. So that would be our right side view. So pretty simple. Yeah, just kind of like basic recursion here, and just simple array properties here. So if we were to kind of calculate the runtime and the space, we need to store the depths and the nodes. So that would be like O of n. And then we're recursively calling this. We're going through the values. So we could have up to v values. And so recursively calling this here. Get depths. Let's see. I think it would actually be linear time, which is faster than I thought. Here's the default dict. We're populating the default dict. And that's in O of n time. We're reaching every node. And then we're iterating through these values. Yeah, it's linear time, it looks like, which is good, which explains why the runtime is running so well on the actual Leetcode when I submit it. Yeah, and then the space would be O of n because we're maintaining this default dict. All right, thanks for watching.